Word on the cloud. It's not working. Oh. Hi, welcome back. Here I am going to be reading chapter 5 from the book Critically Conscious Computing. And before I begin, I want to call out this blog post. I will link in the description below, but it's also here in case the description doesn't follow through. But it's worth being able to explicitly define what's going on when we're reading in different types of reading. So I hope this video is a model of me engaging in type 3 information collection reading and exploratory reading, which aids in both stages 0 to 1 and 1 to 2, the discover and understanding stages of my learning process. So let's get into it. Okay, at the very top, there's an image by Jesse Huyn. Caption: Designing software is like walking the tightrope between technical and social constraints. Chapter 5, CS and Design by Amy J. Coe, and Alannah Oleson. Key ideas from this chapter are: design is deciding what to make, for whom, and why. Engineering is deciding how to implement a design. Computer science is often seen blending design and engineering, but it is mostly an engineering discipline. A teacher's choice of how to address the relationship between design and CS can have profound pedagogical and learning implications on how students see CS and learn its skills. Those are the key ideas in this chapter from the authors themselves. In 1960s, the United States was a time of immense cultural change and political fear. After multiple wars across the world and the growing power of Russia, many in the country and in government were concerned about security in the country's information and communication technologies. At that time, these fears mostly concerned telephones. The US government worried that foreign agents could easily intercept phone calls, or worse, disrupt the telephone networks, preventing military and civilian communication across the country. These fears surfaced a design. How could the United States enable an information exchange that was faster and more secure than telephones? J.C.R. Licklard, a psychologist and computer scientist who worked for the U.S. Department of Defense Advanced Research Projects Agency, had been tackling many problems like this, trying to imagine futures of computing that might achieve these goals of speed and security. One of these futures, he imagined, described a world in which the world's computers, there were just a few at the time at universities and in government, would be connected with each other through a common interchange format, allowing information to be exchanged securely and quickly. He called his design Intergalactic Computer Network and described it as, quote, an electronic commons open to all, the main and essential medium of informational interaction for governments, institutions, corporations, and individuals, by J.C.R. Licklard. What Licklard was doing in writing these memos was design, which Nobel laureate Herb Simon defined as, quote, devising courses of action aimed at changing existing situations into preferred ones. In this design work, Licklard was driven not by questions of how to realize such a network, but questions of what the network should be, who it should serve, and why it should be created. Design, in this sense, imagines possibilities and the ways that might reshape the world. What Licklard was doing was designing the internet. However, because Licklard was one of the directors of the Department of Defense offices, he also had the power and resources to investigate how to make this design a reality. He funded research projects across the world, leading to the founding of the first academic computer science departments, and numerous private labs. The researchers in these departments, in partnership with the government, began an immense period of investigation to answer many how questions that Lickler's visions raised. How would the computers be physically connected? How would information be encoded? How would information be secured? How would information be transmitted quickly? How would information be stored and searched and retrieved? Thousands of researchers and eventually millions of engineers invented answers to these questions over decades, eventually resulting in foundational computer networking ideas like packet switching, transmission control protocol, internet protocol, hypertext transfer protocol, also known as HTTP, the World Wide Web, and browsers. These are the ideas that now power the modern internet, implementing the design that Lickler had envisioned. Unlike the what and why questions that concern Lickler's design concerns, these were all questions of engineering, searching for solutions to well-defined problems. Engineering, in contrast to design, isn't about imagining the future of human experiences, but imagining the technical details of how experiences might be enabled. Similar to how an architect might design a building, but have civil and construction engineers figure out how to build it. In the same way, the software developers of today who envision new social media platforms, new websites, apps, are often not people who engineer such software. Those would be software engineers. This distinction between design and engineering is an important one, not only in design and engineering of internet, but in all of the software. In this chapter, we'll further distinguish these two activities and then discuss common design methods that are used to envision what software will do in order to contrast these methods with the rest of the technical ideas in CS presented in this book. We'll then discuss several ways of teaching design along CS and their trade-offs in helping develop students' critical consciousness while computing. Be right back with some water. Subtitle: Design mindsets. Inside this distinction between design, aka the what, and engineering, the how, are two very important differences in mindset and method. In design, the mindset is one that centers imagination, possibility, ideation, human values, ethics, humanity, politics, society, and justice. Design mindsets are not concerned with whether something is possible or how it might be possible, but rather what should be and how that might be better from what it is now. There's an image subtitled "Deciding what software should do is a different skill than deciding how it should do it." So a woman seems to be working in front of a desktop and drawing some designed symbols. Thinking like a designer requires forgetting how the world works, now to make space for imagining how it might work better, but also deeply engaging with how the world works now to understand how it might be improved and whether design ideas would actually improve it. Design methods are how designers do design. Methods include techniques for understanding problems in the world, speculating about ways to address them, sketching and prototyping solutions, soliciting feedback, all while engaging with the stakeholders that might be affected if a design idea were eventually be engineered. Methods are often based in rigorous theory about how people and technology interact. While Lickler was approaching the problem of networking computers with a design mindset, imagining a future that did not exist yet, his methods were highly exclusionary, only involving the U.S. Department of Defense and a handful of white male professors at elite universities. This is despite the fact that he was fully aware of the risk that computing might only reach a favored few. Quote, "For the society, the impact will be good or bad, depending mainly on the question, will, quote, to be online, end quote, be a privilege or a right. If only a favored segment of the population gets a chance to enjoy the advantage of intelligence amplification, the network may exaggerate the discontinuity in the spectrum of intellectual opportunity. J.C.R. Licklider and Robert Taylor. Of course, we know how this turned out. Licklider's original for-all vision of the internet still has not been realized. Students living in poverty and students in rural communities are less likely to have broadband internet access or computer hardware sufficient for accessing the modern internet because the engineers who built the internet and the policies and businesses that support their work weren't seriously concerned about achieving, quote, for all. People who are blind or low vision often struggle to access the internet because web standards are built assuming sight. And so doing design is no guarantee of doing it in a just, equitable, and inclusive way. In contrast, today's most progressive design methods are increasingly participatory, not only involving intense research with stakeholders in design, but often positioning designers not as decision makers, but facilitators who amplify the design ideas of stakeholders who already know what they need. It's beautiful. It's the heart of teaching, acting as a decision maker, but facilitating. For example, in these design paradigms, designers who might go to the most marginalized stakeholders affected by design, in the case of the internet, perhaps remote rural farmers with no broadband access, youth living in poverty trying to attend school remotely, or blind people with motor disabilities trying to access web services on their smartphones and find ways reimagining computing to make it work for them, and therefore everyone else. Inclusive design methods also focus on helping designers see past their assumptions. For example, one method called assumption ideation involves analyzing how software excludes and does harm. To this ideation, one might consider a particular software service and brainstorm all of the different people, identities, and abilities and contexts in which someone might use it. If this brainstorming is broad, examining a diversity of intersectional identities and cultures, the exclusion and harm becomes more apparent. For example, let's consider the computer mouse, a ubiquitous input device. Who are all the different people who might use it, and what assumptions does the mouse make that might influence how they use it? We might start off with people with disabilities. For example, can a person who is blind use a mouse? No, they cannot track the mouse cursor on the screen. Can a person who has severe motor tremors due to multiple sclerosis use a mouse? Not really, since most mice and operating systems require precise motor movements. Can a person who does not have hands use a mouse? Obviously not. Even this simple ideation reveals that a computer mouse is intrinsically exclusionary, really only working for people with sight and fine motor control over a hand. A designer that prioritizes disability justice would have rejected the idea of a mouse when Douglas Engelbart first invented it in 1961. Design methods can also involve working directly with marginalized people to understand how they use computers. For example, rather than speculating about how people with disabilities use the mouse above, one could connect with people with various disabilities and learn from them. They would find that people who are blind tend to rely on screen reading software, which translates visual content to computer-generated speech. But such software is often poorly supported and hard to configure. They would find that people with severe motor tremors can use a mouse, but it is much more error-prone. Specialized software from research can make using a mouse less error-prone, if only operating system producers would build it in standard. They would find that people who do not have hands do use mice, but would benefit from being able to fabricate their own mouse shapes with 3D printers. These methods, while they might take more time, are much more effective at revealing people's practices and opportunities for design that build on these practices. These methods and many others that designers use all stem from a basic value of empathy, understanding, and justice. These methods view the purpose of design as ensuring that everyone, especially those often ignored and neglected in capitalistic societies, should have computing that works for them. And they seek out insights about how computing is failing them in order to reimagine it. Engineers need these same values, but we shall see in the unit sketch below and the rest of the book, it can be hard to balance the technical constraints and the challenges of engineering with the justice-centered values that should drive design. Subtitle: Engineering Mindsets. In contrast to a design mindset, engineering mindsets are ones that center clarity, precision, verification, correctness, certainty, constraints, and feasibility. Engineers view design ideas not from the perspective of possibility, but implementation. How might the design ideas be realized? How well it would work? How long it would take to build? And how much might it cost? If design mindsets are about envisioning, engineering mindsets are about making. Here we have an image. Three people looking at a screen, and the screen seems to be blown up on the background. And it's captioned, actually there's four people, and there's captioned, whereas design is expansive, engineering is narrowing. Person driving the screen, the computer, happens to be in a wheelchair. Whereas design is expansive, engineering is narrowing. If design mindsets are about envisioning, engineering mindsets are about making. Engineering methods are the ones that involve invention, specification, formalization, testing, proving, analyzing, implementation, and constraint satisfaction. That is not to say that engineering does not involve design methods of its own ways. Many of these activities require a kind of prototyping and iteration of technical solutions, but engineering design is bound by constraints in a way that we might call creative design is not. Let's read that again. Engineering design is bound by constraints in a way that we might call creative design is not. And the history of computer networking shows this. The decades of networking research that led to the internet were immensely creative, collaborative, iterative, and from an engineering perspective, but they all largely stayed within the bounds of the future that Leclerc had envisioned, rather than reimagining the vision as a designer would. It wasn't until many decades later did design resurface, with new visions such as ubiquitous computing, the Internet of Things, cryptocurrency, and distributed networking. In popular culture and in industry, CS is often seen as having elements of both design and engineering. A software developer might be equally interested in envisioning futures as they might be implementing that future. And we see blending in the archetype of the technical entrepreneur, CEO, people imagine that Mark Zuckerberg both imagined and created Facebook, that Elon Musk both imagined and engineered Tesla cars, that Steve Jobs both imagined and created the iPhone. But what is lost in these myths is the historical reality that entrepreneurs are often not doing design or engineering, aside from building early prototypes, if that. For example, Zuckerberg did not invent social media. He was merely mimicking designs that had existed long before his particular vision for it. He also didn't build Facebook himself. He simply prototyped an early vision of it. He hired tens of thousands of engineers to build Facebook we use today. Thus, his contribution involved little engineering and little design. Most of his contribution was entrepreneurial, seeing an opportunity and harnessing it by gathering capital, organizing teams, and setting business vision. Elon Musk did not invent or engineer the electric car. Like Zuckerberg, Musk's contributions were more entrepreneurial, seeing an opportunity to translate more than 200 years of research, design, and engineering effort into profitable manufacturing business. Electric motors and cars were invented far earlier, in the 1920s. Steve Jobs did not invent or engineer the iPhone. Multi-touch displays were invented in academic research labs in the 1970s, and the iPhone in particular was the evolution of a product designer, Tony Fadell, who envisioned the iPod and iTunes Store, and neither Jobs or Fadell engineered these visions. That was the work of many hundreds and thousands of hardware and software engineers who realized the particular design of the iPhone. All of these CEOs have exercised great control over the design of their products, and in that sense, they were engaged in design, but they were not engaged in engineering, and most of their contributions were entrepreneurial. How does computer science relate to engineering? As a discipline, it weaves together many perspectives. It is loosely engaged with design in that it greatly influences what futures we imagine, though it does not engage the many forms of design experience found in schools of design. Parts of CS leverage mathematics greatly, and parts of CS really are an extension of mathematics. However, most of CS is a discipline of engineering, concerned with how to compute things, not what to compute or why to compute it. Questions central to design. And this is clear in the notable absence of conversations about the impact of computing in CS curricula in higher education. Instead, higher education curricula focuses on abstract conceptions of computing, algorithms as abstract procedures, not things that automate human processes, data structures as abstract records of information, not encodings of social phenomenon, artificial intelligence that mimics human ability rather than augmenting it, programming language as expressions of computing rather than tools that people use to control computers. And yet, despite these framings, every aspect of CS has design considerations fundamentally woven through it. What to compute, what data to store, what intelligence to replace, what notions to use to express computation. All of these are design considerations. Because the largely narrow focus of CS on engineering concerns, it would be a mistake to empower the discipline as the sole arbiter of what we do with computers. Design, business, and social perspectives of people and society are important in ensuring computing serves human needs and values. Subtitle: Teaching CS and Design. Because design and engineering are different activities, teaching CS requires teachers to take a stance on the relationship between design and CS. On the other hand, it is empowering and exciting to position students as visionaries of the future. In fact, many of the CS education reform efforts exploit this rhetoric, describing CS as fundamentally about creativity, creation, invention, and impact. For example, Code.org uses the tagline, "Change the World," and focuses much of its curriculum on engaging youth in creatively imagining what to make design, and then teaching youth how to make it, engineering. On the other hand, framing CS as design is inauthentic to CS, which is far more concerned with how to make things than what to make. Therefore, this choice of framing requires more careful choices, as it has direct impact on the aspects of CS are taught and how and what students believe CS is in relation to other activities and professions such as design and entrepreneurship. Let's consider 3 ways of framing CS in relation to design and their pedagogical trade-offs. We'll then present an example unit sketch for the third alternative, which we believe best balances disciplinary authenticity and engagement. So image of a youth with his skull kind of open, not gruesome, but the brain as Lego pieces. And perhaps the same youth manipulating those Lego pieces. The caption to this image by Jesse Queen is, "Teaching CS as design has some benefits, but masks design as a distinct skill." Teaching CS and design as design. One pedagogical option is to equate CS with design. As we discussed, this is inaccurate. It ignores design as its own independent discipline, and it erases the processional practice and expertise of professional designers, many of whom have more power over what software is created than software developers do. Is processional a word that I just don't know? Or do they mean to say professional? Hmm. However, treating CS as design has the major advantage of being empowering. For example, one way to position CS is as fundamentally expressive discipline in which one imagines futures and creates them, much like a visual artist might have a particular vision for an experience and then create it by harnessing technologies like illustration software or digital cameras. Framing CS as an expressive discipline centers students' creativity and interests by prioritizing learning contexts that center the students' creative visions and by being responsive to your students' interests and concerns. These values are largely consistent and constructionist views of learning, which embrace student-centered discovery, learning that leads learners to construct knowledge to understand the world around them. Further, prior work around broadening participation in computing suggests that design-related activities to help engage diverse groups of learners, such as women and students from underrepresented cultural groups, emphasizing the creative and social aspects of CS by conflating it with design enables students to engage with computing topics in ways that feel authentic and personally relevant, infusing their creations with their own values and perspectives. There are numerous methods that follow this framing. For example, Coffey's book, Connected Code, Why Children Need to Learn Programming, describes a range of methods for engaging students in browsing student projects on the Scratch programming platform, copying a project, learning how it is built, and then modifying it to imagine their own vision. With enough skills, with Scratch as a tool, students can feel empowered to envision their own experiences and create them on Scratch. Learning to be resourceful in learning from others, both in the classroom and online, these constructionist methods to learning can allow students to express themselves, to build upon their interests, and learn aspects of CS that are deeply situated in personally meaningful projects. While this method can be powerful, it does subordinate many of the foundational ideas in CS. For example, imagine you believe it is crucial for a learner to understand how to use programming languages, while loop to help them pass the APCSA exam, which assesses knowledge of loops extensively. What if the learner doesn't need to use loops to create their vision? What if they don't need the program at all to express their vision, instead simply taking someone else's program and replacing the images and sounds in it? What if a student encounters a need for loops, finds them too confusing, and decides to change their vision to avoid requiring them? As many investigations have shown, this is precisely what happens when design activity is centered over engineering activity. Students will spend immense time envisioning a software project, creating media for it, and imagining its experience, all fundamentally design activities, but rarely engage in engineering in any depth and thus learn little about CS concepts. Equating design and CS can also contribute to teaching and learning difficulties if the boundaries between the two disciplines are not recognized and made distinct. Prior work suggests that the pedagogical content knowledge educators develop and rely on to teach computing is meaningfully different than from the pedagogical content knowledge for teaching software design, since PCK is domain and topic specific. Educators who conflate the two disciplines might struggle to teach each other well due to a lack of clarity on what they're actually teaching about. Students may also encounter difficulties separating design and CS, and the two are too closely intertwined during instruction. Recall that design questions ask what and why, while engineering CS questions largely ask how. Answering these distinct kinds of questions requires different approaches and techniques. However, students who are told that they are learning CS when they are actually doing design tend to apply engineering mindsets to design problems. For example, slowly building their way to a design but compromising their ideas in order to work around technical difficulties. When that doesn't work, they get confused and frustrated. Sometimes this frustration leads to backlash. CS students might assert that it is not their responsibility to consider broader societal and ethical contexts when they are only building technology, refusing to critically consider the ways in which their programs might impact others. Boy, do we see that coming to life in modern Silicon Valley and the broader techosphere. Another risk with equating CS with design is that it ignores essential aspects of design activity. For example, design is centrally concerned with understanding human experiences and values in the world and envisioning futures that serve them. Consider, for the example, the design of a video game, which is a common genre of creative coding projects in Scratch. Game designers need to consider the ethics of a video game addiction, the potential for abuse in social games, the stereotyping of race and gender in game characters, the balance between artistic freedom and social responsibility, and the glorification of violence. Framing CS as a fun way to create games both de-emphasizes the engineering depth of CS, while only shallowly engaging the ethical depth of design. This approach might also risk perpetuating conceptions of design that are fundamentally exclusionary, creating things like computing without incorporating the perspectives and needs of diverse stakeholders. When students are not prompted to design for users with goals, desires, and contexts that differ from their own, they often implicitly end up creating something that aligns only with their own needs, abilities, and preferences. Teaching CS as design without engaging deeply with design's foundations discounts the need for creators to think about the broader impacts of their creations. Finally, equating CS activities and design activities tends to misrepresent the reality of CS-related roles in the workforce, leading students to pursue CS careers when they really might be more interested in design roles. Software engineers typically don't design software, they build it based on what designers have designed. User experience, UX designers, interaction designers, and even business-minded product managers determine what software should do and set requirements accordingly. Clarity around what counts as design and what counts as CS can help students make informed decisions about future education or career choices. Here's an image. The AP calendar class contains methods used to calculate information about the calendar. You write 2 methods of the class. I think these are questions from the AP CS exam. So the subtitle is Engineering Centered Pedagogies Focus on Problem Solving, as in this AP CS exam prompt. I'm going to take a break for now. Okay. To be continued. I will finish the rest of this chapter in a follow-up video. Thanks.